Non-resonance Raman spectroscopy makes use of the change of polarizability induced by certain vibrations. A polarizable molecule will oscillate in an electric field, and an oscillating dipole radiates with the frequency of vibration. The induced dipole moment is given by the following. The approximations made in defining Raman scattering are that light scattering is independent of the geometry of the molecule, and that scattering is only caused by electrons and not the nuclei. This is reasonable if the electronic transitions have a much larger energy than the vibrational transitions, and that the energy of incident light is larger than the vibrational transition energy. Non-resonance Raman spectroscopy makes use of the energies between electronic and vibrational transitions. Electronic transitions typically take place above 12,000 wave numbers, and vibrational transitions typically occur below 3,000 wave numbers. Absorption of an incoming photon results in a transition to a virtual state. A virtual state is not an eigenstate, but is allowed to occur due to the uncertainty principle. The extremely small lifetime of the virtual state results in a large uncertainty in the energy of the virtual state and allows for energy to be conserved. The vast majority of scattering comes from relaxation to the initial state and results in inelastic scattering. This is called Rayleigh scattering. If the final state after relaxation is higher in energy than the initial state, then inelastic scattering occurs. This is called a Stokes shift. If the starting state is a populated excited state, then the final state may be lower in energy, and this results in a signal called the anti-Stokes shift. The spectrum obtained from a non-resonance Raman experiment will take the following shape. The Rayleigh peak dominates the spectrum and occurs at V0. This is because this signal comes from an elastic scattering event. The main peaks of interest are the Stokes and anti-Stokes peaks. The Stokes peaks occur at energies lower than the Rayleigh signal, and the anti-Stokes peaks occur at energies higher than the Rayleigh peak. It is important to note that what matters is the frequency shift, not the absolute value of the Stokes and anti-Stokes peaks. Usually, there is no sample prep requirement for Raman spectroscopy. This technique can be applied to numerous materials such as films, powders, and solutions with very little or no sample preparation time. Analysis can also be carried out through many containers such as glass bottles, plastic containers, and more. Water does give a Raman peak, but it is a weak Raman scatterer. For example, a 4% alcohol in water solution will yield a Raman spectrum containing signals from both the alcohol and the water. The water spectrum will be about the same intensity as the alcohol. In surface-enhanced Raman spectroscopy, Raman signal from the molecules absorbed on certain metal surfaces can be 5 to 6 orders of magnitude stronger than the Raman signal from the same molecules in bulk volume. Appropriate surface substrate is very important. The most popular and universal substrates used for SERS are electrochemically etched silver electrodes as well as silver and gold colloids with average particle size below 2 nanometers. In Raman spectroscopy, the excitation energy comes in the form of a photon. Because Raman spectroscopy uses a photon beam, the penetration depth of the sample is varied heavily by the sample's optical properties. Materials with better optical properties will have larger penetration depths. The beam strength also plays a role in penetration depths. For example, a sample of silicon using 633 nanometer beam will have a penetration depth of 3 micrometers. With a beam of 785 nanometers, the penetration depth is 12 micrometers, and at 532 nanometers, it is 0.7 micrometers. The spot size can also be controlled by aperture. Raman is best suited when a non-destructive chemical analysis of a sample is required. It is very sensitive to chemical bonding, so it is advantageous to use Raman when minute changes in molecular bonding must be detected. Almost any material can be used with Raman spectroscopy with the exception of pure materials. As Raman uses light near the visual range, any sample that can be held in glass can be studied, including liquid and gaseous samples. Due to the wide range of suitable samples, Raman spectroscopy is used for many applications, including chemical analysis of DNA, defect analysis of semiconductors, and identification of gemstones. There are several limitations in the Raman technique. First of all, the calculations may not yet be used to resolve the true vibrational nature of all the systems, and we still need more knowledge about the interatomic interactions. Also, the types of structural model may be limited for real-world objects. There are also a few disadvantages that this technique cannot be used for, such as metals or alloys. The Raman effect is very weak, so that the detection needs a sensitive and highly optimized instrument. The fluorescence of impurities or the sample itself can hide the Raman spectrum. Sample heating through the intense laser radiation can destroy the sample or cover the Raman spectrum.